Welcome back, everyone, to the Algebra Graph Theory Seminar. This week we have Emanuel, Sylvia, talking about strongly regular cospectral vertices on trees.
Um, Hi everyone, my name is Emanuel, and today I'm going to talk about strongly cospectral vertices on trees. So today I will start talking about strongly cospectral vertices, remember the definitions, and talking about some related theorems. Then I'm going to talk about the main problem, that is, if there exists a tree containing three strongly cospectral vertices. Then I'm going to talk about my constructions to try to solve this problem. Um, then I'm going to talk about the consequences of this construction. And then some questions that appeared at the workshop. Most of the references of this talk are from the book, the unpublished book of Gabriel and Chris called Graph Spectra and Continuous Time Quantum Laws. Okay, let's begin. So let X be our graph. In the following examples, let X be P3. P3 has this adjacency matrix, and this is the spectral decomposition of the adjacency matrix. So it's the sum over the eigenvalues times the idempotents. So for this example, the eigenvalues of P3 are square root of 2, 0, and minus square root of 2. And the idempotents are 1/4 of this matrix, a half of this matrix, and 1/4 of this matrix. But before jumping to the definition of strongly cospectral vertices, we need to define some things first. So let E sub I be the characteristic vector of vertex I. We say that two vertices A and B are parallel if for each idempotent, the projections of the eighth column of E sub R and B column of E sub R, if they are parallel, we say that the two vertices are also parallel. So just in our example, we can see that the first and the third vertices of P3, the two end vertices, they are parallel because the columns of the idempotents, they are all parallel. In this case, they are equal. In this case, they are one minus the other. And in the third case, they are also equal. And there is a theorem that says that if two vertices A and B are parallel, if and only if the poles of this rational function are simple. We're going to use this theorem later in this talk. So this rational function is the characteristic polynomial of x after removing vertices A and B divided by the characteristic polynomial of x. Okay, those were the parallel vertices. And there is a straightforward conclusion from here. That is that if all eigenvalues of x are simple, then every pair of vertices of x are also simple, are parallel, sorry. Okay, so now let's jump to the cospectral vertices. So I say that two vertices in B are cospectral if the AA entry of each idempotent is equal to the BB entry of the corresponding idempotent. So in this case, for the first and the third vertices, we can see that the AA entry is equal to the last entry for each of the idempontents. And again, as with the parallel vertices, there is a theorem related to the definition. So, which in this case is where the name comes from. So we say that two vertices are cospectral if and only if the characteristic polynomial of x after removing A is cospectral, or is equal to the characteristic polynomial of x after removing B. That is, x minus A is cospectral with x minus B. And for those of you guys that, just to remember, two vertices are similar if there is an automorphism that maps one of the vertices to the other. Therefore, if we remove this vertex from our graph, if we remove vertex A, the remaining graph is going to be isomorphic to the graph we get after removing vertex B. And therefore, if x minus A is isomorphic to x minus B, the two graphs are also cospectral, and therefore, similar vertices are cospectral. Okay, and now we have what we need to define strongly cospectral vertices. So two vertices are strongly cospectral if they are at the same time parallel and cospectral. So for this example, the two end vertices of P3, they are parallel and they are also cospectral. Um, and again, the theorem related to the definition is that two vertices A and B are strongly cospectral if and only if um, the eighth column of each idempotent is equal to plus or minus the bth column of the same idempotent. So of course, from this definition, we can see at least one of the directions here from this theorem to this definition. Of course, A and B are parallel here. And since they are idempotents, we can again see that the AA entry is going to be equal to the BB entry because of this plus or minus sign. And here we don't have a straightforward definition as a straightforward conclusion as before. But this theorem is going to be very useful to us later in the talk. So two vertices A and B are also strongly cospectral if and only if there is a orthogonal matrix Q such that Q is a polynomial in a rational matrix, and Q maps A to B, and its square is equal to the identity. Okay. So this definition of strongly cospectral vertices, some theorems related to it. And now let's go to the problem. So the problem here is if there exists a graph with three mutually strongly cospectral vertices. And actually for this problem, there is an answer, and the answer is yes. So for P2, Cartesian P3, vertices A, B, E, and F, they are similar. You can think about an automorphism that maps A to E, A to F, or every pair of them. And besides that, the eigenvalues of this graph, they are all simple. And therefore, A, B, E, and F at this graph, they are strongly cospectral. So not only three, we found four vertices strongly cospectral. But now maybe we can think about finding this triple at other classes of graphs. So the question here is if there exists a tree containing three mutually strongly cospectral vertices. And in this case, the answer is we don't know. I actually run an algorithm, and no tree up to 22 vertices has this structure, this triple of vertices. But maybe we have two options here. Or we prove that this structure could not occur at a tree, or we're trying to find this triple of vertices. And the last option is what I try to do during this talk. So, okay, before trying to construct this type of tree, let's just think about why the star on three vertices is not strongly cospectral. So why A, B, and C of S3 are not strongly cospectral. So we said that similar vertices are cospectral. In this case, A, B, and C, they are the three of them similar vertices. Um, but what happens is that they are not parallel. And the question is, why they are not parallel? And the answer comes from this theorem. So if two vertices are strongly cospectral, then every automorphism that fixes one of the vertex must also fix the other vertex, which it's not true for this case. So for example, there is an automorphism that's going to swap vertices A and B, but it's going to fix vertex C, and therefore C cannot be strongly cospectral neither with A, neither with B. And this occurs for every pair of vertices here. Um, so okay, this theorem kind of say to us that not every similar not every pair of similar vertices are going to be strongly cospectral, but maybe we just choose the wrong tree. Maybe there is a tree containing three similar vertices, which hopefully they're going to be not only cospectral but also strongly cospectral. So okay, let's look at the automorphism group of A3 and trying to find if there is going to be, if we can find this triple of vertices. So the automorphism group of A3 is based on two operations. The first operation is called branch transposition, which is basically you fix one of the vertices, and you pick two of its branches and you map one branch to the other. Therefore, you're going to swap the two branches. So in this case, we could, for example, swap vertex A with vertex B. The second type of operation that occurs when the tree is bicenter is a reflection along the center of the tree. So in this case, vertices E, D, and F can be mapped to vertices B, C, and A by a reflection along this bicenter of the tree. And if you combine these two operations and try to think a little about three similar vertices at E3, you end up realizing that if you have three similar vertices, A, B, and C, which are mutually similar, there is going to exist an automorphism that swaps two of the vertices and fixes the other one. Therefore, there cannot be a tree containing three similar and strongly cospectral vertices because of the existence of this automorphism. Okay, so this implies that we can no longer try to construct trees with a triple of similar vertices, but we still need the vertices to be cospectral. So what we want to do now is to construct trees with cospectral non-similar vertices. Um, and that's the idea of what's coming up. So we have this tree. So we have vertices A, B, and C. This is going to be the structure of our tree. A, B, and C, they have one edge incident to T4, which is also a tree. A is connected as any way as you like to T1, B as any way as you like to T2, and C as any way as you like to T3. So T1 is basically the limbs of the vertex A at this tree. And the question is when A, B, and C are mutually strongly cospectral. And just as an example, if T1, T2, and T3 are the null graph and T4 is K1, we have S3. And okay, now let's try to construct the cospectral non-similar vertices. So suppose we have now this construction. So only caring about two of the vertices. So if we have vertex A attaches to T1 and vertex B attaches to T2, and we join A and B by a simple path. The claim here is that if A and B are strongly cospectral, if and only if this ratio occurs, if this ratio is equal to this ratio. That is, if phi of T1 divided by phi of T1 union A is equal to phi of T2 divided by phi of T2 union B. A important thing about this is that it do not depend previously on the tree in the middle, on the size of the path, for example, in this case. And the other important thing is that we don't need A and B to be similar. We just need to find the right choice of trees such that this ratio is equal to this ratio. And I'm just going to show this theorem here. So, but before showing it, I'm going to use two useful lemmas. The first lemma is just going to be useful to this specific theorem. So if we have a construction very similar to before, but X doesn't need to be a tree, can be any type of graph, and Y the same for Y. If we pick a vertex A from X and a vertex B from Y, and join A and B by a simple path, if they are cospectral at Z, then they're also going to be strongly cospectral. Therefore, the condition of parallel, so the two vertices to be parallel, we just have it for free. So we just need the two vertices to be cospectral. And the second lemma is the one sum lemma. So here we have a vertex x, a graph x, and a graph y. We pick a vertex a from x, and we identify this vertex as another vertex a from y. So in this case, if we delete vertex a, we're going to be separating the resulting graph into two components, one containing x minus a and the other containing y minus a. So if we have this type of graph, then we can write its one sum, which is decomposing the characteristic polynomial of z into this expression, which is not the most beautiful expression, but is an expression that only depends on phi of x minus a, y, x, and y minus a. And it's going to be very useful to us for all the rest of the talk. So okay, and how we're going to apply one sum to our graph. So this is our starting graph. This is the one sum lemma. And we want to show that two vertices are cospectral. So we're going to write phi of t minus a. At t minus a, we have two components, one containing t1 and the other containing the rest of the graph. And the rest of the graph is simply the path b and t2. Our graph x for the one sum is going to be the path connected to b, and our graph y is going to be b connected to t2. So in this case, b appears in both x and y, and we're going to apply one sum at b. And the resulting expression is this one. I do the same thing for vertex b, for phi of t minus b, and we have this expression, and we want to show, verify when these two terms, these two equations are going to be equal. After we distribute the terms here inside the parentheses, we're going to have some identical terms. So for example, phi of t1 times phi of pn plus 1 phi of t2 is equal to phi of t2 times phi of pn plus 1 phi of t1. Therefore, we can discard these terms. The same thing occurs with the last terms. And therefore, phi of t minus a is going to be equal to phi of t minus b if and only if this product is equal to this product. Phi of pn occurs in both products, so we can discard it. And therefore, we reach our conclusion. So at our construction, vertices A and B are going to be strongly cospectral if and only if this ratio is satisfied. And now I'm going to use precisely this type of ratio to find the cospectral non-similar vertices, and then construct a tree with a bunch of them. And now I just wanted to open a big parenthesis because I wanted to just for a moment focus on this construction and some consequences of this construction with the tree and the vertices joined by a simple path. The first consequence of this construction is that if A and B are strongly cospectral, not only the two vertices are going to be strongly cospectral, but also the symmetric inner vertices of the path. So if we have vertices x and y symmetric along the path, if A and B are strongly cospectral, then x and y are also going to be strongly cospectral. And the proof of this theorem is just follows by applying one sum again at x and at y. And well, okay, so we know that x and y are strongly cospectral if A and B are strongly cospectral. And we also know something about strongly cospectrality. We know that if two vertices are strongly cospectral, there's going to be a matrix Q that is a polynomial in A and that maps A to B. And the question here is, okay, so Q is going to map A to B and B to A. But what about the inner vertices of the path? Q is also going to map X to Y. And the thing is, if we have this construction, there is going to be a matrix Q, polynomial in A, that swaps A and B, but also the vertices of the path. So, for example, if we have this tree, which follows from the previous construction, So in this case, vertices 4 and 7 are strongly cospectral. T1 here would be P3 union K1, and P2 and T2 is going to be the two paths on three vertices. We connect T2 to B and T1 to A, and we connect A and B by a simple path. So in this case, 4 and 7 are strongly cospectral. By previous theorem, 5 and 6 are also strongly cospectral. And the thing is, in this case, there exists a matrix Q that maps A to B, but also X to Y. And the theorem says that there is always going to exist a matrix like that. And I want to show this to you guys. So how is the proof? So this is our graph. We have vertex A, vertex X, Y, and B. And let sigma r be the sign of the mapping from column A to column B of the R idempotent. So sigma r is plus or minus 1. And we know that this equality holds if and only if there is a polynomial that's going to map theta r to sigma r, and it's going to map when applied to A, E sub A to E sub B. So, okay, we know that this equality holds because we know that A and B are strongly cospectral. And let X and Y be the two vertices of the graph. And let sigma r prime be the sign of the mapping from column X to column Y. So sigma r is just the sign related to A and B, and sigma r prime is the sign related to vertices X and Y. And we're going to construct this polynomial as follows. So if theta r belongs to the support of X, but does not belong to the support of A, then we're going to map theta r to sigma r prime, which is the sign of X and Y. Otherwise, we're simply going to map to sigma r. And the claim here is that this polynomial is going to map A to B, but also X to Y. And the thing is, it is going to do this if for every eigenvalue that belongs to the support of both X and Y, sigma r is equal to sigma r prime. If this condition is true, then this is a valid polynomial that is going to map A to B, but also X to Y. And what we are going to do now is show that sigma r is equal to sigma r prime for every eigenvalue in the support of both X and Y, X and A. And how we prove it? We are going to observe to the AX entry and to the BY entry of each of the idempotents, such that the theta r eigenvalue belongs to both the support of A and X. So the AX entry of E sub r, since E sub r is just a projection, it's simply going to be the inner product of the eighth column with the X column, which after we replace this column by the column of B and the column of Y with the respective signs, we're gonna have this equality. So the entry AX is going to be equal to the entry of BY if and only if sigma r times sigma r prime is equal to 1. What happens if and only if sigma r is equal to sigma r prime? Therefore, if the entry AX is equal to the entry BY, this would imply that sigma r is equal to sigma r prime, which is precisely what we want. So, okay. And how you're going to try to show then that those entries are equal? By, again, looking at the entry, but in another way. So this equality, it's just a way to determine the entry AX of the idempotent R. There is a story about this equality that recently was called neutrino identity. I don't know if this is the best name because I don't know what a neutrino is, but it's going to be very useful to us. So we might verify that the entry AX is going to be equal to the entry BY if the term inside this root are equal. So since A and B and X and Y are cospectral, this term phi of X minus A is going to be equal to phi of X minus B, so we don't need to care about it. Phi of X minus X is going to be equal to phi of X minus Y, so we again don't need to care about this first product. And therefore, the entry AX is going to be equal to the entry BY if this product phi of A minus phi of X minus AX is equal to phi of X minus BY. So if this holds, then the two entries are equal. So we just need now to show that this holds. And how we're going to do this? By the following method. So let L be the size of the path. So the size of the path containing A and B. For L equal to 2, A and B are adjacent. So therefore, X is equal to B and A is equal to I. So the claim holds. And for L greater than 2, let D be the distance from A to X. We want to show that this term is equal to this term. So phi of X minus AX can be decomposed into two terms, one containing T1, another term containing the path, and another term containing the rest of the graph, which is precisely what is written here. Since the multiplication is associative, we can pass this term to the end and realize that this product is actually equal to phi of T1 union a path of smaller length union T2, but after removing vertex A. Since A and B are cospectral at this smaller graph, we can replace here A by B, and we can realize that this product is actually equal to phi of X minus By. And therefore, the two terms are equal. So just what we did here, we showed that phi of X minus Ax is equal to phi of X minus By, because this would imply that the entries of the idempotents, the entry Ax and the entry By, are equal. And this would imply that sigma r is equal to sigma r prime. And this implies the existence of a matrix Q that swaps A and B and also X and Y. Okay? And just a comment here. Um, Not every matrix which satisfy those constraints that swaps A and B are also going to swap X and Y. So here previously I did a choice of the mapping for the eigenvalues that are not in the support of A. So not always the matrix of the strong ecospectrality theorem that I said earlier, not always that matrix is going to swap A and B. But between all of the matrix that swaps A and B, there exists one that's going to swap not only A and B, but also X and Y. And okay, now I close my big parenthesis, and let's turn back to constructing cospectral non-similar vertices. So one observation about the proof of this relation is that the middle graph does not need to be a path. So we were connecting A and B by a path, but actually, if A and B are connected to this middle graph and they are cospectral at this middle graph, that is Y union A union B, if A and B are cospectral at this graph, then after we add x1 to A and x2 to B, since they're cospectral in the middle graph, they're going to be cospectral after the adding of x1, x2, if and only if this relation holds. So the thing is that now we don't need the tree Y to be a path. This can be any tree containing, for example, our vertex C, but as long as A and B are cospectral in this middle tree, we can add the limbs, and then A and B are going to still be cospectral if this relation of the limbs holds. And that's how we're going to construct our trees. And just as an example, um, the tree in the middle is just a singleton. Vertices 4, 14, and 16 are going to be our A, B, and C. We connect 4 to, we connect A to 27, B to 27, and 16 to 27. And the rest of the vertices are the limbs of A, B, and C. Um, the tree in the middle, it's just S3. So the vertices 27, 4, 14, and 16, they induce the S3. Of course, they are cospectral in S3 since they are similar. And I choose the limbs in such a way that after adding it, the three vertices are cospectral, even though they are not similar. And actually, that is a collection of limbs that we could choose here and add. Um, I have like 50 of those triples of limbs. So there are lots of examples, but unfortunately, if we connect just as this way with S3 in the middle, the three vertices, they are just cospectral. They are not strongly cospectral, which made me a little sad. But what we're going to see now is why the three vertices are not strongly cospectral. So if you guys have any questions. So, okay, let's see why these three vertices are not strongly cospectral. So here is the middle tree. So T4 connected to A, B, and C. And here is our construction. We choose T1, T2, and T3 in such a way that A, B, and C are strongly cospectral. Um, but the thing is, the tree that I used in the middle, it was S3. And A, B, and C, if they are mutually similar at this middle tree, they cannot be strongly cospectral after we add its limbs, um, which is quite sad here, but at least we have a proof of why they cannot be strongly cospectral, even though they are cospectral and non-similar. Um, and for this proof, to prove this theorem, I'm going to construct another tree, T prime, uh, which is as follows. So this is our middle tree. We start with this tree again. So we know that if A, B, and C are similar at this middle tree, that is an automorphism that swaps two of them and fixes the other. So let's say that this automorphism swaps A and B and fixes C. If we attach to C its limbs, that is connect T3 to C, we can extend the automorphism and still having an automorphism that swaps A and B, but fixing C. Therefore, C cannot be strongly cospectral with A and B. And now if we add T1 connected to A and a copy of T1 connected to B as the same way as we connected to A, at this graph, T prime, A and B, they are still similar. And therefore, we can again extend the automorphism, and A and B, we can again swap them by in fixing C. And therefore, A and C cannot be strongly cospectral at T prime. A, B, and C cannot be mutually strongly cospectral here. Um, but okay. And my claim here is if A, B, and C are strongly cospectral at T, this would imply that A, B, and C are strongly cospectral at T prime, which is an absurd. So let's go now to the proof. So basically what I need to show is that if B and C are strongly cospectral at T, they cannot be strongly cospectral at T prime. And that's exactly what I'm going to do. So first, let's show that if B and C are parallel at T, they cannot be parallel at T prime. The two vertices are parallel if and only if the zeros of this rational function are simple. But this rational function, we can rewrite it as another form. So if we remove vertices B and C, we have three components, one containing T2, one containing T3, and another containing the rest. And if we apply one sum to phi of t, applying one sum at vertex B, we have this expression. I'm highlighting here the terms which contains T2 and B. So from this expression, because B and C are cospectral at T, but also at the inner tree, I can replace this term divided by phi of T, T2 union B divided by phi of T2. I can replace it by phi of T1 union B divided by phi of T1. And of course, I can replace phi of T2 divided by phi of T2 by phi of T1 divided by phi of T1. So, and you guys may realize that if we apply the same steps that we did here, but with T prime, this is exactly where we get. So the two rational functions for T and T prime, they're actually the same. And therefore, if the zeros are simple at one of them, they are also going to be simple at the other one. And therefore, if B and C are parallel at T, they are also going to be parallel at T prime. And now for the cospectrality, since B and C are cospectral at T, we can rewrite phi of T minus B and phi of T minus C. So this first term is just phi of T minus B, and the second term is just phi of T minus C. We again apply one sum at this term here, and we get this expression where I'm again highlighting the terms that contain T2 and B. If we divide both sides by phi of T2, I get a unique term containing phi of T2 union B divided by phi of T2, which, as you guys know, it's equal to phi of T1 union B divided by phi of T1. And we're going to use it to show, to get from phi of T minus B to phi of T prime minus B to phi of T prime minus C. So this is phi of T prime minus B. If we remove T1 and B from T prime, we get the same thing as removing T2 and B from T. Therefore, these two terms are equal. And if we apply one sum at this term, if we apply one sum, from previous slides, we know that this term is equal to this expression. So I just replaced the expression here, and I multiplied phi of T1 inside the parentheses, and I get that phi of T prime minus B is equal to phi of T prime minus C. And therefore, I showed that if B and C are strongly cospectral at T, they're also going to be strongly cospectral at T prime, which is an absurd. And now, just to finalize the talk, during the workshop, I presented a poster with this subject, and there some questions arrived. So, for example, I was talking with Sophia about the general construction of sets of strongly cospectral vertices. So P2 Cartesian P3 gave us a set of size 4. P2 Cartesian P3 Cartesian P4 gave us a set of size 8. But for larger sets, we don't quite know how well these Cartesian products should relate. Therefore, the question that arrived was that if there is a systematic way of constructing sets of size, let's say 2 to the power of k, of strongly cospectral vertices by choosing the right combination of paths for the Cartesian product. Another question that arrived that Harmy came to see my poster, and she has lots of results about strongly cospectral vertices related to any type of matrix. And therefore, she asked if there is a triple of strongly cospectral vertices in a tree with respect to the Laplacian matrix. I don't know the answer for this problem yet, but I guess that we would face some similar problems since we still need the vertices to be parallel here. And therefore, that the automorphism condition, it should still hold in here. Crystal and Mark, after Mark presenting about strongly fractional cospectrality, strongly fractional cospectral vertices, they asked if there is a tree containing a triple of strongly fractionally cospectral vertices. And this question is specifically interesting because strongly fractional cospectrality is not a transitive relation. So in Mark's talk, he was talking about the path on 5D minus 1 vertices, that the vertex D is strongly fractional cospectral to its symmetrical vertex and also with vertex 3D. So the path is a tree. We have a vertex, strongly fractional cospectral with other two vertices. So maybe we have found the triple. But the truth is that the two vertices that this graph is strongly fractional cospectral, they are not strongly fractional cospectral with each other. Therefore, since this is not a transitive relation, for paths, this structure does not occur, and which is quite interesting, at least in my opinion. So, okay. And this question arrived in a meeting with me, Chris, and Gabriel. That Chris showed me the Schwenk tree, which is a tree that does not arrive from my construction of cospectral non-singular vertices. And at this tree, we have a pair of strongly cospectral vertices because they are cospectral and the eigenvalues of this tree, they are simple. And therefore, maybe instead of focusing on cospectral vertices, we can or we should focusing on constructing trees with parallel vertices. For example, trees with simple eigenvalues. And lastly, Crystal, she liked the subject about strongly cospectral vertices in trees. She saw my poster and she gave me some ideas of how to try to show that there is no triple of strongly cospectral vertices in a tree. And the idea was to relate the Q matrix with the automorphism of a tree and maybe reach some conclusions such as, okay, if Q maps A to B, B to C, and C to A, maybe this would lead us to an absurd. So these are other paths that we could lead to try to solve or advance in this problem. And that's it. Thanks everyone for your attention. I watched these seminars since the beginning of the pandemic, so I learned very much with you guys and your awesome research areas. So thank you very much.
Thank you very much. Are there any questions?
Can you go back to your previous slide?
Of course.
Just the last point there. Have you thought about how to do this?
I was thinking a little about this, but yeah, the first idea that came in my mind did not work, so I don't know yet.
Okay. This idea came from Crystal, you said?
From where?
From Crystal?
Yeah.
Okay. Well, thanks for the talk. It was very good.
Emanuel, I have the question. Sorry.
Go ahead, Harry.
Yeah, because what you did with respect to adjacency, right? Matrix.
Yeah.
And the techniques mostly employed characteristic polynomials and the ratios and everything, right?
Yeah.
Do, do you think the same? Do you think we can use the same technique for the Laplacian? Right, because most of these are adjacency, right?
Yeah, so to try to construct the cospectrum on similar vertices, but with respect to the Laplacian matrix.
I have a comment related to that. It's a lot harder to get PST using the Laplacian than it is using the adjacency matrix. And I think the problem is because you're working with vertices, if you do what Sen did in her thesis and use pairs, you can get quite a bit of state transfer. So in a sense, you're getting transfer between edges. And so it's possible when you work with Laplacian, you should be thinking in terms of edges rather than vertices.
Okay, so thanks, Chris.
Thanks, Chris, yeah.
So will your approach works for strongly fractional cospectral vertices?
I haven't tried,
okay.
but the cospectral vertices that I created, they're also fractionally cospectral, right?
Yeah.
But just
you
look
have more room to play with it, right?
Yeah, just look to strongly fractionally cospectral vertices. I tried, since I already had a similar code, I tried to look for the maximum of trees to find the triple of strongly fractionally cospectral vertices. But again, I haven't found any such tree up to 15 vertices, I guess.
Okay.
And what surprised me was that not even the paths they had the triple of strongly fractionally cospectral vertices.
Emanuel, so in K2 Cartesian P3, you have 4 strongly cospectral vertices, right?
Yep.
Emanuel and Sophia, is it possible to get just 3 pairwise strongly cospectral vertices in Cartesian products? Or does it always have to be a power of 2?
I don't know if with Cartesian products, but Gabriel, he showed us an example of a graph which contained 3 strongly cospectral vertices. But I don't know how did he constructed that graph.
It was not me that actually found the example, but I'm pretty sure it was exhaustive search on regular graphs from 10 to 20 vertices, something like that. And the graph was a 18 vertex 3 regular graph, I think.
That would have been Fidel then.
I would think that with Cartesian products, you could not get 3.
Or odd in general, you think?
Yeah, well, if you're looking at the vertices of, so the boundary vertices, the vertices that have lower degree than the rest, then they will all be strongly cospectral to each other when that happens. So you have to actually get a power of 2. But this is kind of just a feeling. I think this is true.
Okay.